Okay, so now that we've looked a little bit at our complex numbers and graphing them in the complex plane, the next thing we're going to look at is the polar form of a complex number. So this basically just uses what we've already learned about polar coordinates and just applying it now to complex numbers. So let me just remind you for a minute about our polar coordinates. So polar coordinates, remember, are basically saying instead of plotting a point as x and y, we're plotting it as a point r and theta. So it's dependent on your radius of r and your angle of theta. Okay, so think if you have a complex number in rectangular form or standard form, you would know an x and a y, and you would need to find r and theta. Okay, well, if you recall from when we did our polar coordinates and our conversions back and forth between polar and rectangular, we know two formulas. X is equal to r cosine theta, and y is equal to r sine of theta. Okay, so if you think about your complex number in standard form or rectangular form, x plus yi, let's go ahead and just make these substitutions in here. So for x, I'm going to substitute in r cosine of theta. And for y, I'm going to substitute in r sine of theta. Okay. All right, then if we just clean this up a little bit, we can factor out our GCF, which would be an r. So we'd be left with r times the quantity cosine of theta plus I sine of theta. Okay, so this right here is the polar form of a complex number. Okay, but I just wanted to show you guys where that comes from and that it all ties back into what we already know about polar coordinates. Now, one thing that we need to pay extra close attention to here is when we're using the polar form of a complex number, there's two conditions that we have to satisfy. The radius has to be positive, okay, so we're not allowed to use a negative radius when we're dealing with complex numbers. And the angle has to be between 0 and 2 pi. So we also have to have a positive angle. Okay, so let's go ahead and take a look at a couple examples of switching back and forth between rectangular form or standard form and our polar form. Okay. All right, so our first example here, we have the complex number 1 plus I. So the first thing I'm going to do is just sketch this complex number. Okay, I highly recommend that you start by sketching your complex number because it's important to know what quadrant it falls in, because when we're solving for our angle theta in a minute, we have to have the correct quadrant in order to have the correct angle. Okay, so 1 plus I would be in quadrant 1. I'm just going to sketch my little right triangle right here. Okay, so 1 plus I means our x is 1, and our y is 1. And what we need to find is our angle theta and our radius of r. Okay, now again, going back to what we learned about polar coordinates, you may recall that in order to switch from rectangular into polar, we had two formulas. Okay, one is just our Pythagorean theorem, x squared plus y squared is equal to r squared. Okay, that's what's going to help us find our radius. And then the other is just the tangent. Tangent of theta is equal to y over x, and that's going to help us find our angle of theta. Okay. All right, so first solving for r, we would have 1 squared plus 1 squared is equal to r squared. Or if we solve that out, r is equal to the square root of 2. And again, we're only choosing the positive radius on this one. So we're not doing the plus and minus, we're just going with the positive. All right, and then similarly, to find our theta, tangent of theta is equal to 1 over 1, which would, of course, just be saying tangent of theta is equal to 1. So if we're looking in quadrant 1 for an angle where tangent is equal to a positive 1, that would be the angle pi over 4, okay? So this is why it's really important to plot your point first, because had we not known that this was in quadrant 1, then our angle could have been either pi over 4 or 3 pi over 4, but only one of those is actually correct. The only correct angle is the one that fits the quadrant of your original point. So make sure you plot that point before doing anything else so you know the quadrant that you're supposed to be in. Okay, so if we put this together, again, remember this is our polar form of a complex number. Just copied that down from above. So we're just going to rewrite all of this in that polar form. So our z is going to be equal to the square root of 2 times the quantity cosine of pi over 4 plus I sine of pi over 4. So that is our final answer. Okay. All right, let's go ahead and take a look at a second example. I'm going to actually jump down to part C. I'll leave part B for you guys to try on your own. All right, so same as the last one, very first thing we want to do is plot this point in the complex plane. So 3 plus 4i is again going to be in quadrant 1. All right, so draw your little right triangle. X is 3, y is 4. So we need to find the radius and we need to find our angle theta. Okay. All right, so again, to find the radius, we just use Pythagorean theorem. So 3 squared plus 4 squared is equal to r squared, or that would give us r is equal to 5. And then to find our angle theta, we'll use tangent. Tangent of theta is equal to 4 over 3. All right, now unlike the previous example, this is not an angle on our unit circle. So in order to solve for the angle, we're going to have to use the inverse tangent. So theta is equal to the inverse tangent of 4 over 3. And we're going to need to plug this into our calculator. Okay. Now I would like an angle in radians on these, so I'm going to make sure my calculator's in radian mode. And then I'm just going to plug in the inverse tangent of 4 over 3, and we're going to get approximately 0.927. Okay. Now this is an angle in quadrant 1, like we want it to be, so that's going to be our final answer. But just hypothetically, if we had had an angle over here in quadrant 3, then you would need to say add 180 degrees in order to get your answer. So make sure always that the angle that you have is within the correct quadrant. Okay, so now just putting this together, we will have our number is 5 times the quantity cosine of 0.927 plus I sine of 0.927. Okay. All right, so that will be our final answer. Okay. All right, so then going the other direction, if we have a complex number in polar form and we want to rewrite it in rectangular form or standard form, you might see it referred to as, this is actually really easy. All we need to do is evaluate our trig functions at the given angles. Okay, so in this case, for example, we have 3 times the quantity cosine of 210 plus I sine of 210. Okay, so we just need to evaluate our trig functions at 210 degrees. Well, that's easy enough. That's a unit circle angle. So cosine of 210 degrees is negative root 3 over 2. And sine of 210 degrees is negative 1/2. Okay, now if these weren't unit circle angles, then you could plug them into the calculator and get a decimal approximation. But as long as these are angles on your unit circle, I want you to give me an exact value. Okay, so if it's a unit circle angle, give me an exact value. If it's not a unit circle angle, then you can plug it into the calculator and give me a decimal approximation. All right, so then we just need to distribute our 3n. So we would get negative 3 square root of 3 over 2, and then minus 3 over 2i. And that would be our final answer. Okay, so again, if you're going from polar to rectangular, just evaluate your sine and cosine and distribute in the radius. Okay. I'll leave example B for you guys to try on your own. All right, so the very last thing that we need to do with these complex numbers is we're going to look at how to find the product and the quotient of complex numbers in polar form. Okay, so if you have two complex numbers, I've gone ahead and said Z1 is equal to R1 times the quantity cosine of theta 1 plus I sine of theta 1. And similarly, Z2 is equal to R2 cosine of theta 2 plus I sine of theta 2. Okay. All right, so we have these two formulas here then. So firstly, if we want to multiply two complex numbers together, we start by multiplying our R values, so R1 times R2. Then we still have the same polar form as before, but what we do to combine our angles is we add them together. Okay, so we have cosine of the angle theta 1 plus theta 2 plus I sine of the angle theta 1 plus theta 2. The easiest way that I can help you remember this is think about your exponent rules, for example, right? If we think about this exponent rules for a second, and we have something like b to the power of x times b to the power of y. Well, when you're multiplying together, how do you combine your exponents? You add them. So this would become b to the power of x plus y. So it's the same sort of situation here. When we're multiplying together our complex numbers, we add the angles. Okay. All right, well then similarly, if we're dividing our complex numbers, start by dividing your r values, and then you subtract your angles theta 1 and theta 2. So again, this follows exponent rules. Do you think about b to the power of x divided by b to the power of y? How do you combine your exponents? You subtract them. This would be b to the power of x minus y. So when you're finding the product and the quotient of complex numbers in polar form, the way that you combine your angles is basically the same as the way that you combine your exponents when you're looking at your exponent properties. Okay. So the reason I tell you these memory tricks to remember them is I do expect you to memorize these formulas for the test. These are not going to be on your formula sheet, so make sure you have these general rules memorized. Okay. All right, so let's go ahead and take a look at an example. All right, so we have these two complex numbers. Okay, so Z1 is 2 times the quantity cosine of pi over 4 plus I sine of pi over 4. And Z2 is 5 times the quantity cosine of pi over 3 plus I sine of pi over 3. So we want to find both the product and the quotient of these complex numbers. Let's go ahead and start with the product. Okay, so if we're multiplying Z1 times Z2, we're going to start by just multiplying our R values. So 2 times 5 is going to be multiplied out front. Okay, and then since we're finding the product, we're going to add our angles. So that would mean cosine of pi over 4 plus pi over 3, and then plus I sine of the angle pi over 4 plus pi over 3. So just remember, when you're multiplying complex numbers, add the angles. Okay, now of course we need to actually combine these. We need to add them together. So if you need to do the scratch work over here on the side, you can. So pi over 4 plus pi over 3. And of course, remember when you're adding or subtracting fractions, just find a common denominator. So in this case, our LCD would be 12. So just get that common denominator. So we would have 3 pi over 12 plus 4 pi over 12, which would be 7 pi over 12 as our new angle. All right, so simplifying this, 2 times 5 is of course 10. And then we'll have times the quantity cosine of 7 pi over 12 plus I sine of 7 pi over 12. And that is our final answer. Okay. All right, let's go ahead and also find the quotient. So Z1 divided by Z2. right? So in this case, we start by dividing our R values, so 2 divided by 5. And since we're taking the quotient, we're going to subtract our angles. So we'll have cosine of the angle pi over 4 minus pi over 3, and then plus I sine of the angle pi over 4 minus pi over 3. Okay. All right, so then we need to go ahead and combine these angles. So again, think common denominator. Pi over 4 minus pi over 3. Same LCD of 12. Okay, so 3 pi over 12 minus 4 pi over 12 would give us negative pi over 12. Okay, so this would be 2/5 times the quantity cosine of negative pi over 12 plus I sine of negative pi over 12. Okay. All right, now we're not quite done though, because if you go back up and look at our definition that we had originally for the polar form of a complex number, I told you that the radius has to be positive, but also the angle has to be positive. The angle has to be between 0 and 2 pi, okay? Right now, our angle is negative, so we can't leave this as our final answer, okay? Now, instead of using the even-odd properties in order to get rid of this negative angle, which would be one possibility, we're instead going to think of what's the coterminal positive angle for this. Okay, so just to kind of give you a visual here, I'm thinking negative pi over 12 is down here in quadrant 4. I want to figure out what's the coterminal positive angle that's also in quadrant 4. The reason why it's important to do it this way is because this is representing a complex number, which is represented as a point in the plane. So we have to be extra careful to make sure that we keep that point within the same quadrant. Okay, so all I'm going to do is I'm going to take my original angle of pi over 12, or negative pi over 12, excuse me, and I'm going to add 2 pi to it. And again, just think common denominator. Oh, I don't know why I just multiplied by 4. That was wrong. Times 12 over 12. Okay, so get that common denominator. So this would be negative pi over 12 plus 24 pi over 12, which would be 23 pi over 12. Okay. All right. So this is going to be for our final answer, 2/5 times the quantity cosine of 23 pi over 12 plus I sine of 23 pi over 12. All right, guys, so that is our final answer. Okay, so again, I just want to reiterate here that if your answer comes out with a negative angle, add 2 pi to that angle in order to come out with a positive angle instead. Okay. All right, so I'm going to leave example 6 for you guys to try on your own. All right, so that is going to be the end of our video on the complex plane.